Great. Okay. Yeah. Welcome everyone to the fourth session of the Python Bootcamp.
Hey, I think something happened to your microphone, at least for me.
Sorry?
Something happened to your microphone, but I can hear you now.
Oh, can you hear me now?
Now I can. I don't know if it happened to everyone else.
Oh, okay. Okay. Perfect. Yeah. Thank you. And welcome everyone to the fourth session to the Internet Computer Python Bootcamp. We have total 6 sessions today and then next week, Friday, and we finish on Saturday. This session, again, is taken by Jordan Last. He's the Demergent Labs founder and CEO. Also, you can connect through our Discord channel or the Demergent Labs Discord channel as well. I have problems with my slides. Okay. Also by the KU Computer Science Club, also organizing by Finance Club and the Demergent Labs. The fourth session again, and we have the proof of attendance or soulbound token by the artist Ejidoval. To get this token at the end of the bootcamp, you need to attend at least minimum 5 sessions. Follow the Twitter ICP.North, the Twitter of the ICP.Hub North America, the official one, and then deploy Hello World that Jordan explained a few episodes before, or chapters, and plus additional feature. All the information about this bootcamp is in our YouTube channel. Is uploading all the episodes. And then yesterday, Jennifer Tran explained us how to request free cycles to build on the mainnet on the Internet Computer blockchain. If you missed yesterday the session, I recommend you go to our YouTube channel and check it out. It was like the first 10 minutes of the session, how to request free cycles. And yeah, let's start coding. Again, I would like to see like more activity in our Discord channel, more questions. If you are starting to dive in more in the Hassel book, it's important because Jordan can explain everything, but I expect like people have questions, of course, and I expected like these sessions are useful for you guys and more interactive. And that's all from my side. Over to you, Jordan. Thank you so much.
Okay. Here we go. So yeah, yesterday we were finishing up HTTP requests, right? HTTP requests. So sorry, the canister applications on the computer can receive HTTP requests, right? For example, acting like a server, or they can actually make HTTP requests acting like a client. That's where we left off. So, yeah, if you remember, we used the management canister, the HTTP request. This is an example of talking to Ethereum. And then to receive a request, you make a query method and you call it HTTP request. So we'll pick up from there. We're going to move on to chapter 15. We've talked about the management canister quite a bit, but let me just go over it again. The management canister. This is a virtual canister that provides a lot of system functionality. So let's just show you all the methods on the management canister. Okay, so these are the methods available to you. We have Bitcoin get balance. This allows you to actually get the balance of a Bitcoin address from the live Bitcoin network, which is really nice. The Internet Computer has what we call a direct integration with Bitcoin. There are actual Bitcoin nodes running alongside the internet computer nodes, essentially. And the internet computer nodes come to consensus on a part of the Bitcoin blockchain, I suppose. So you can get the balance of an address. You can get information that helps you determine what fee you should set for a Bitcoin transaction. You can get UTXOs for an address. Let's go see. Get UTXO args. Yep, for an address. The UTXOs, that's just how Bitcoin works. You can study that, but those are known as unspent transaction outputs. Very fundamental how Bitcoin works. And then, why is this out of alphabetical order now? Oh, that's it. Oh, there we go. Bitcoin send transaction. Once you have a signed transaction, you can send it directly to the Bitcoin network. So that's really cool. The internet computer has the ability to read certain information from the Bitcoin blockchain and to actually write, essentially, right? Send a transaction to the Bitcoin network. Very cool. How do we achieve this, though? Because generally, if you want to sign a Bitcoin transaction or an Ethereum or any transaction on any blockchain, you need to have a private key. But storing a private key on an internet computer node probably is not very secure because the node operators can technically read everything. But there is some more functionality on the management canister that lets you create threshold ECDSA keys. So if you call ECDSA public key, you can actually generate a threshold ECDSA key. ECDSA is the elliptic curve, or is the signing algorithm that Bitcoin and Ethereum use, and a bunch of other blockchains use. And threshold ECDSA means that when you ask for one of these key pairs, you don't actually get the private key back. The private key is actually stored on a special subnet, which last time I checked has 28 nodes. And each node only has a share or a piece of that private key. So the private key is never all together on any one machine. So you don't have to trust one node operator, right? So then it inherits a similar security model to subnet. So you can generate these keys. You can also sign with these keys. So if I want to sign a Bitcoin transaction, I would create the transaction, and then I would call this sign with ECDSA method that will sign it with the ECDSA subnet. And then I can call Bitcoin send transaction and pass that in, and it'll go to the Bitcoin network. So that's some of this. That's the Bitcoin stuff and the threshold ECDSA functionality that the management canister provides. Canister status will allow you to retrieve, and remember, these are just methods, right? So canister status, you just call it, and then what do you pass in? You pass in arguments, which is basically a type dictionary. In this case, it just has a canister ID. What will it return? The canister status result. So it will tell you things about a canister whose ID you pass in. For example, the status. Is it running? Is it stopped? Is it stopping? Is it stopped? Settings. The controllers of the canister. Those are the principals, or basically the key pairs that are allowed to basically have unilateral control of the canister. Compute allocation, memory allocation, freezing threshold. Those all have meanings that you can look up. So yeah, canister status is something you can grab. You can delete a canister. You can deposit cycles into a canister. get an ECDSA key, do HTTP request. You can install a WASM binary into a canister. Those provisional things, I don't remember exactly what those do, but you can look those up. You can get randomness like we talked about. Signing, of course, you can start up your canister, stop a canister. Uninstall code that removes the WASM binary and wipes the memory of the canister, I believe. And you can update settings of canisters that you're a controller of. And I think we're out of, yep. So these are just Python things. So that's what the management canister does. If you want more information, you can always go to the examples here and check out the management canister example. And it just shows you how to use a bunch of the methods. So, for example, create canister, right? Here it is. You call management canister.create canister, pass in the arguments. In this case, you need to pass in some cycles, and then you get your result. Just like yesterday, we talked about doing cross canister calls. Same thing. This returns a call result. It'll have an OK or an error property. And yeah, so there you go. It's just a canister. It just has a bunch of methods. Also, remember there's a reference section where you can see the APIs available. So the management canister section, and you can go look, and it basically just gives you an example of how to use that method. So that's the reference section. Okay. I mean, that's basically chapter 15. These chapters, by the way, in the end here, are a little bit sparse. We're not done with them. So we both basically just put in an example. So any questions about the management canister before we move on to chapter 16? And I will go over here to look at the chat. Or you guys can just unmute yourselves.
Jordan, I have a question.
Yes.
I know the threshold ECDSA is really good to connect also with Bitcoin, with Ethereum, but I have questions about the replicas, how it works exactly, the key shares that provides the information. And because I know like 1/3 of the subnets have to be approved, or how it works exactly to, I'm a little bit confused about the thresholds ECDSA and the private ECDSA. If it's the same, is not the same, and how it works exactly in the subnets.
Yeah, so you said threshold ECDSA, and what was the other thing you said?
Is a private ECDSA is the same?
I don't know what private ECDSA is. Is that, what is that?
I think it's...
Yeah, I only know of threshold I think I know what you're saying. Just the private key?
Yeah.
Or okay, yes.
I call it private ECDSA, but it's a private key, right?
Yes, I'll explain that. So, okay, let me stop sharing for a second to just explain the concept. So, in public private key cryptography, we have what's called a key pair. And you basically have a public key and a private key. These are just two numbers, basically, that are linked together with a mathematical algorithm. So if you have a public key, it tells you that you're able to verify that somebody owns a private key based on certain operations that the private key performs. For example, if you give me a piece of data, like a PDF or something, I can take my private key and I can sign it. Signing with the private key generates another cryptographic number, basically. I can give you that signature, and I can give you my public key, and you can run a verification that tells you that I own the private key that the public key corresponds to. And that's how all of this blockchain stuff is working for the authorization, at least. So, for example, a Bitcoin transaction, if I say I want to send some Bitcoin basically from my account to your account, I have a private key, and the Bitcoin network understands, has the public key available, I believe. I mean, I think it must. And what I do is I create a transaction. It's just basically a piece of data saying, send this here, do this, whatever. It has a special format. I sign it with my private key, and then I broadcast it to the network. When a Bitcoin node receives a signed Bitcoin transaction, it uses the public key. I'm assuming this is how it works. Bob Bodley would know much more because, honestly, I kind of left the Bitcoin community years ago because I thought Ethereum was more exciting. But so it should work like this, basically, though. So the Bitcoin network will, a Bitcoin node will verify that the public key and that transaction and the signature are all correct. If the signature doesn't correspond to the public key, it means that I did not have the private key that corresponds to the public key. So that's generally how public-private keys work. But if you notice something is every time I have to own that private key to sign with it. And generally speaking, that private key is one number stored in one place, right? For example, if you have like a Ledger or a Trezor hardware wallet, generally your private key is just stored and available on that device in one place. If someone steals your device, obviously you can have backups, but if they steal your device, they technically have your private key and they can sign with it. So that's the problem, is that a private key, like a public-private key pair, it's a central point of failure by default because it's in one place. So the internet computer threshold ECDSA essentially takes the private key and splits it up into a bunch of pieces. And each node only has one of the pieces. And here's the thing, it's a little bit better than just splitting up into pieces because it doesn't matter which nodes, like you can lose some of the nodes. You need 1/3 of the nodes, and you can have any 1/3 of the nodes, and that's all you need to sign. And so let me share my screen again, and I'll show you the subnet. But does that help?
Yeah, help. But in that case, each node have a different private key?
Yeah, they don't. Yes, they have a different share. They're called shares. They have a different share of the private key.
Okay, but
all the shares are equal, essentially. You just need 1/3 of the shares.
Okay.
Yeah.
But you mentioned the keys split, right, in different portions, right, or different information.
Yep.
If we lose one of this information, other nodes have also this information because you said it's only one. We need 1/3.
You only need 1/3. Yep. Exactly. And that's what makes it robust, or more robust. So if I'm not mistaken, the threshold ECDSA subnet is either this subnet or this subnet. I think it's this subnet. And so you can see all the node operators, right? And we don't have to trust any one of these node operators. We only need to trust that they won't collude with each other. 1/3 of them won't collude. Let's see if we can see. Yeah, there are 5 canisters on here. I wonder if it will show the canisters. Yeah, but yeah. So the threshold ECDSA, it's all happening on, I think, the subnet. It's one of these 28 node subnets. And there's a share here, and there's a share here, and there's a share here, there's a share here. Right? There's a share on each. I believe they all have their own shares. And the shares are never collected into one place. They perform a threshold protocol where they communicate with each other to basically generate a signature. That's my understanding. So does that answer that well enough?
Yeah, of course. Thank you, Jordan. Thank you so much.
Yep. Okay, so that's the management canister, and it does not get any more questions. So we will move on to chapter 16, the canister life cycle. So this word life cycle, imagine a human being, right? We have a life cycle. We start off in our mother's womb. We grow. We're born. We become toddlers. Then we become adolescents. Then we become adults. Then we become old. And then we die. That's our life cycle. Canisters have a life cycle as well, but it's way, way simpler. And there's not as much emotion involved, right? So there's basically there are three methods that we can use to hook into the life cycle of a canister, or basically to put functionality in that will run at different points of the canister life cycle. The first, so let's get this going while I explain it. So we'll copy this in. I'm going to restart my replica from scratch so that this canister is completely new. And I'm going to run dfx deploy. Okay, so the first method that we have available to us to hook into the lifecycle is called the init method. You just import the init decorator and you decorate your method with it. It's pretty self-explanatory. This method will now run the first time that the canister has code installed into it. So basically the first time that you run dfx deploy, this method is going to run. So there's all kinds of things you might want to do to initialize your state only one time. Perhaps you are creating a token and you want to set the initial balances, right? You might want to do that in the init method. You could maybe just do that globally, but the init method maybe is the place that you want to do it. So yeah, this is the most basic point here, is it runs on the first canister install. Now, you can obviously deploy to canisters over and over and over again, right? And every subsequent deploy after the first one is going to run these two methods. Pre-upgrade runs just before the code, the WASM binary is swapped out and the heap is wiped. Whenever you deploy, remember, the heap gets wiped and then your WASM binary is exchanged for the new WASM binary. Pre-upgrade runs right before that. So let's say you're not using stable B-tree map and you're using the more low-level stable memory APIs, which we haven't talked about yet, but you are able to write into the stable memory location that stable B-tree map writes into using a very low-level API where you can just do everything in bytes. You can grow your memory, read your memory, get the current size right into memory. So if you need super low-level functionality, you might, during pre-upgrade, write a bunch of stuff into stable memory, and then your heap is wiped, your code is changed, and then in post-upgrade, this runs post-upgrade is basically init, but it's just not the first init. It's not the first time you've deployed. Every subsequent deploy after init is going to run post-upgrade. And so, yeah, so for example, if in pre-upgrade you wrote into the stable memory area, in post-upgrade you could read from the stable memory. Generally, if you're using stable B-tree map, you shouldn't really need to use pre and post upgrade too much, but who knows? I'm just explaining the functionality that's there. There might be other use cases. And yeah, there's a few use cases that we have found in our examples. Basically, sometimes you might want to pass some information in to the canister while you're deploying, and I can show you that. Okay, so let's take a look. This was the first time we deployed, right? So our init method executed, and it said it runs on first canister install. So it's exactly what we expect. Now let's deploy again. Notice I didn't change the code. So there is a chance that because the code didn't change, it won't actually trigger the full upgrade. But I don't remember if Kybra is still subject to this. So we'll just see what happens. If it doesn't change the code, or yeah, if it doesn't change the WASM binary, then we'll just change the code. Okay, cool. So we got exactly what we would expect. Pre-upgrade runs before canister upgrade, and then post-upgrade runs after canister upgrade. So right before everything was changed, this ran, and right after everything changed, this ran. And now if we deploy again, it's never going to run init again. It will always run pre-upgrade, and then it will run post-upgrade. Now there are a couple. Well, there's one more major concept to learn about init and post-upgrade, and that is that you can actually pass parameters in on these. Pre-upgrade does not take any parameters, and notice they all return void. Right? You never return anything from init, pre-upgrade, or post-upgrade. And I just want to prove to you. Yep. So it's always going to do pre-upgrade and post-upgrade from now on. So let's say you want to pass in something. For example, let's say, yeah, remember how we made another canister the other day? So let's just make one real quick. Let's say you have a canister called canister 2, and it has a query method. Yeah, let's just call it like read message, just turns a string. All right. So the problem is that to use canister 2, we have to initialize it, and we need to pass in canister 2's principal, its identifier, right? Okay, can you see a possible problem here? What if I don't know what the identifier is yet? I would have to hard code it, but if I hard code it, then it's hard coded. So what you might want to do is pass this in as a parameter. Canister 2 principal. There you go. Now keep in mind, if your init and your post upgrade parameters, they need to be exactly the same. They should not be different. Because post upgrade is basically just init, right? Okay, so now I have this here, and what I can do is when I use canister 2, up here, I'll just initialize that to nothing. Oops, and I'll just say, yeah, I'm not sure it's going to let me do that. That's annoying. There we go. Yep. Okay, so now I'm able to set this globally. And so when I go to use it, as a read canister 2 message, yeah, pretend we're doing the whole thing. Gotta import everything. So okay, now I can create a canister 2, and I can pass in the canister 2 principal. And then I can do all the stuff that we did, right? Otherwise, result that okay. Oh. Did I not do this correctly? Can't do that. Okay. Let's see what's going on there. Okay, well, I was just doing this too. Oh, there we go. Okay, so yeah, so now when I create this main canister here, Kybra Hello World, I can dynamically set the canister to principal. Because, for example, your principal locally is going to be different than your principal in production, most likely. So if I'm deploying locally, I can set to one thing. If I'm deploying to production, I can set to another. So let's start this over, and I can show you how you pass things in. Okay, now if I try to deploy, it should break, telling us, hey, you need to actually pass in a principal as part of your deploy. Gotta upload it all again. Okay, so what I'm hoping to see is over here an error message telling us that a init failed. Aha, okay. So what happened here? Reject code destination invalid. Yes, the Rust Python interpreter could not be initialized. Init or post record has most likely trapped. Check your local replica logs if available. Look over here for errors. Unfortunately, it didn't give us a nice error, but pretty sure it's simply this. Okay, I don't actually have an ID for canister 2, so we'll just use the management canister ID as just like a default. It's called argument. DFX deploy. Oh, I guess I have to give it a name. I have to reference it by name by passing an argument. Okay. Okay. Basically, now this is how you pass in parameters to an init post. Say -- argument, and then you pass it along. And that's going to be the canister 2 principle right here. Well, I hope this works. Oh dear. Oh, you know what? Wait, this is a very important concept. Sometimes if you get into weird states, like you don't know what's going on, it looks like it should work, you just might want to restart your replica with this -- clean flag. Just remember that, because that will just completely wipe the state of your replica and start it over from scratch. So I'm not sure if because we did a partial deploy on a init that it, partially worked or something and it broke. So yeah, I'm just starting it over, trying it again. If it doesn't work, hopefully it will. But this is the general concept here. And it will run that again. So while that's deploying, let's go into some caveats. Oh, huh. So there are some caveats here, especially in Kybra. There are just some very technical, fundamental problems with the Internet Computer Protocol that give us some interesting limits that we have to work within. And to work around these limits, we have some caveats. So for init and post upgrade, let's go read the caveat for the params. Okay. For example, if you add parameters to your init or post upgrade methods, I forgot about this. You will need to manually add these parameters to the service in your candidate file for the first deploy to succeed. Interesting. Anytime you change these parameters, you'll need to manually add these changes into your candidate file. That's sad. So, yep, I'm really glad we documented this. The first time you deploy, basically we need to go right here, and we need to manually say that it requires a principal. And we started our replica over clean. And now we will deploy. And then it should be good after that. Okay, some other nuances within it post-upgrade. In order to allow for larger Kybra WASM modules and to enable the Python standard lib, we had to introduce some trade-offs into the post-upgrade processes. The under the hood, I mean, I don't know if you guys need to really know all this now, but just keep in mind that there are caveats. Chapter 19 is dedicated to all the caveats. I'll just keep reading this one though. The under the hood Rust init function of your application candidate is never called directly, only the post-upgrade function. So you just have to keep in mind that the actual init function of your canister, like the actual WASM or Rust function under the hood that everything's compiled into, is not called. We actually only call the post-upgrade function. That post-upgrade function will then call your Python init function. So just keep that in mind. And apparently it's called in a timer callback. So technically speaking, requests could come in during that timer callback. So yeah, if you are going to deploy an actual production system, you might need to keep this in mind. When deploying to a local replica, errors from your init or post upgrade will be logged from your replica and not from the DFX deploy process. That's why, oh, by the way, it did succeed this time. So you just might need to look over here in addition to over here to see errors. Unfortunately, when you deploy to mainnet, if you do have errors in init or post upgrade, you will not be able to see them. And then your canister will go through the following main steps when deploying. And this is really technical under the hood, but first a deployer canister wasn't binary will be deployed to the canister. Then your application wasn't binary will be chunk uploaded to the deploy canister along with the Python standard library. And finally, the deployer canister will call install code on itself with the full application wasn't binary. It's just, these are all the under the hood crazy things that we had to do to get this all to work. And it just deviates a little bit from Rust or Motoko or from TypeScript from JavaScript. So I just put that in there. Okay, but yep, so that finally worked, right? We were able to pass our argument in, and it should be stored here on the heap now. If we run post upgrade, it will just do the same thing. So every time you want to change these parameters, you just need to go to your candidate file, manually add them in, and then deploy. Okay, that's the canister lifecycle. I mean, I guess another caveat is IC.caller. That usually is going to give you the principal that actually deployed the canister. For example, it would give you the principal of your DFX identity. But in Kybra, IC.caller from an init or post circuit is the canister's own principal. That's just another caveat. All right, any questions about the canister lifecycle? You guys understood that all perfectly? Okay, cool. Well, it's all here in chapter 16. And there are various examples in the repo that show init pre and post upgrade as well. Okay, last thing we'll go over for today is something called timers. Basically, a timer is it allows you to do cron job-like things. Basically, what you can do is you can say, hey, I want you to run this function at some point in the future. If you are familiar with JavaScript, it's very similar to the JavaScript set timeout function. And yeah, you can look at this example. It's a little complicated, but it shows you most things you could do, but we'll just go over real quick everything from scratch. So let's start this over. Okay, we're going to just do some basic timers. So we need to import update, and we need to import duration, and I think we need to import timer ID, and we need to import IC. Here we go. We'll make a method called setTimer. We'll just return void. I'll need to import void. Okay, this is the most basic way to do this, but we're just going to set a timer for the future. We pass in a delay, so how many seconds in the future you want the thing to run. And then you pass in a function that you want to run. So I'll pass in a lambda. It takes no methods, and it will just print. Oh. Man, did I get the lambda wrong? All right, well, instead of being fancy, I'll just do this. Just call this the timer callback. We'll also return void timer executed. Well, what is this error? Oh, maybe the lambdas don't work. Okay, the point is you pass a function. There we go. Let's start to deploy this. So what this does, from the command line or from the web UI, we're going to call the setTimer function here. This will call IC.setTimer. IC is a class with a bunch of internet computer functionality. This is not the same as the management canister. The management canister generally is for, I guess, asynchronous operations. This is for synchronous operations. I mean, some things are asynchronous, but a lot of these things are just synchronous. For example, caller, right? Which will give you the principle of the key pair that's executing your function. Can it decode for, or can it encode for encoding a candidate string into bytes? Can it decode, blah, blah, blah. There's a bunch of things you can do. In this case, we're going to use setTimer. Okay, I think it's because we need to delete that. Here we go. So like I said, with the timer APIs, you can implement things like cron jobs, right? You can say, hey, at this point in the future, I want you to do this thing. Or you can set kind of like, I don't know, like a clock or a poll, which I'll show you in just a second, where you can say like every 30 seconds or every minute, I want you to run this, or you could check something. And this allows you to do things without a human being having to trigger something. Okay. Now I'll just do this from the command line. DFX canister call. Kybra hello world. What do we call it? setTimer. All right. 5 seconds from that, we should see it print right here. Ah, there we go. Timer executed. And we can call it again. Timer executed. Perfect. Doing exactly what we said. Now, there's another API. It's called setTimer interval. It's just like setTimer, except it will do this on an interval. Now, after we call this, every 5 seconds, it's going to say timer executed. Okay, here we go. Pretty soon, we should see that it's just going to keep printing timer executed over and over and over. There we go. Yep. Okay, let's change this to 1 so we can see it more often. Oops. There's something else you can do. You can actually clear the timer. So let's make a global variable called timer ID. And I'm going to just set the global timer ID equal to what set timer interval returns, which is a timer ID. And a timer ID under there is just an int. Then, if I want to cancel this interval, I can call IC.clearTimer, and I can pass in the timer ID that I stored. Probably don't need duration for that. So let's deploy. Actually, let's change this to something else. Execute timer so we can just see the difference easily. Deploy again. Now we have the ability to set a timer and clear timer. Clear timer works for set timer interval and it works for set timer. Also keep in mind that every time you deploy, all of your timers will be wiped. So that's a good reason to use init and post upgrade maybe. If you have some timer interval that you expect to always be running, you might call it an init post upgrade. You can also do it globally. All right, set timer. Okay, every second there it goes. And then we'll do clear timer. And we should see that it stopped. Yep, it stopped. All right, that's all for today. Any final questions before we're done?
Yeah, Jordan, I have a question related with the canister life cycle.
Yeah.
Yeah, is it because the canisters consume cycles to computation, to performing computation? But for example, for storing data, I know like per year we have to pay $5.5 per gigabyte. But this is another thing, right? A part of the $5.5, we need to also have cycles in the canister.
Yeah, just to store data. That's what you're asking about? How much it costs basically just to keep data in there? Yeah, I'll show you right here. Let me find this and I'll share my screen. Okay, so yeah, if you just go to the internetcomputer.org documentation, gas and cycles cost, there's a table here.
Mm-hmm.
And if you look for right here, gigabyte storage per second. So it just looks at how much you have stored. And then every second, if you're in a 13-node subnet, every second, where'd it go? It will charge you 127,000 cycles. So every second, it's just charging cycles, basically. The more you store, the more cycles it charges per second.
Okay, and the $5.5 is just like a calculation?
Yeah, I assume if you add this up over a year for 5 gigabytes, then it turns out to be around $5.
Oh, okay.
Yep. And that's just for 13-node subnet. So like if you have more nodes, it would be more expensive. If you had fewer nodes, I assume it would be less expensive.
Okay. And also another question, if the cycles is run out, maybe you started something and you forgot, you receive a notification before to run out the cycles. And also once it's run out and the cycles like disappear, is a way to recover the information or the data, or it's totally disappear on the blockchain and you
So,
cannot recover again?
yeah, you don't get a notification, but your canister will freeze. There's a threshold set and a cycle threshold that's set. If your canister goes, I guess, at or below that threshold, the canister will freeze, meaning it will. I don't remember exactly what happens if it's all query methods and all update methods stop. I think everything just stops and it says like, hey, this is frozen. That gives you hopefully time to add more cycles. But if you don't and you run out, then your canister will be, as far as I know, entirely deleted and gone and not recoverable. The ID will stay there, like your canister ID, I believe, always stays there. And your cycles, well, your cycles are gone, so it doesn't matter. But yeah, all your information is wiped. There's no way to get it back.
Mm-hmm. Yeah, thankfully we have can scale, right? The project can scale. I think
Can scale?
yeah, in can scale, you can see the cycles that you have per canister, and if you need to add more cycles, I think the project can scale, like send you a message or in some way.
Yeah.
And
I think that's another project that they're doing. Can scale is the scalable database, but yeah, we need lots of projects like that.
Byron Becker, right? I think it's
Yeah,
Byron.
Yes. Yep.
Yeah. Can scale, or maybe it's another project with Byron.
Yeah, but yeah, yep, they're working on something like that. Yep.
Yeah.
But yeah, it's an interesting challenge. It's something that Bitcoin definitely doesn't have to deal with. Ethereum doesn't currently have to deal with it, but Ethereum's plan is to introduce state expiry, which will do the same thing. It will delete data over time, more or less. So it's just a problem that you can't just expect to be able to store data forever for free. Mm-hmm. So yeah, we just got to come up with solutions.
Yeah. Okay. And in your opinion, is a good solution, the internet computer cycles for you? Compared with other blockchains?
It's basically the same as other blockchains. It's just chosen to approach it in a different way. So I think it has some benefits, has some drawbacks. Ethereum is moving towards the same thing with account abstraction. So it's basically the same. Everyone's doing the same thing. It's just Dfinity chose to by default. They chose a different default, I guess. By default, the developer has to pay. On Ethereum and Bitcoin, by default, the user has to pay. But yeah, Ethereum is moving towards allowing other people to be able to pay on your behalf as well. So
make more sense, right? The end user, if they use applications or enter in the internet computer, don't pay anything, right? And it's like maybe more in the developer side. If you want to build something, you have to pay for a computation, right? I think it's a better approach.
I don't know if it's better.
Trade-off. Yeah.
In my opinion, it just depends on what you're doing. I think it just depends. Like, I think it depends. So, because sometimes I think sometimes you want the user to pay. Sometimes I don't know. It brings different challenges. So, like on Ethereum, yeah, you can deploy something and it just runs, right? It's fine. You don't have to do it. You don't have to worry about it. On the internet computer, that's not the case. So it's a little bit difficult. But also, you don't want to have Ether to do everything, right? So, but that's what account abstraction on Ethereum will do. It allows other entities to pay gas on your behalf. So everyone's kind of doing the same thing, in my opinion, when you really look at it.
Yeah, for the end user, it's like you don't have like surprises on ICP, right? I remember with MetaMask, I bought like a token or an NFT, and it was like the cost of the gas, it was more expensive compared with the token that I bought, right? And it was like, man, this is crazy. Like, at least in ICP, I assume like cycles are stable, and like a fixed cost. It depends also maybe the ICP token, right? But it's not like fluctuate a lot, and you don't pay like a lot today, tomorrow morning, and then in the evening less. It's more stable, right? In that case.
Yes, so far, yep, it's designed to be stable. So yeah, that in that aspect, it's better. But you're also getting a lot less replication out of that, right? So, and then we've had projects on the intercomputer just randomly get deleted. So it's just it's different trade-offs.
Randomly deleted the canister?
Yeah, there've been NFT projects. There've been a couple, I think, that I know of where they just forgot to put cycles in, and then everything got deleted.
Yeah, that's the problem. If you cannot recover, or you don't have like a time, maybe a days or a week or something, or a time during like you can maybe have again and reset the canister and put more cycles. That's bad news, right? Because imagine if you only have storage there and you don't use your canisters in a daily basis or pretty regularly, you can forget, right? Like put like more canisters, and
Yep.
I'm not a little surprised that it's not any way to recover if the canister is deleted and all the data storage and all the information is completely lost. Right?
Yeah, they're working on well, they're working on canister backups, but I don't think that solves the problem of if you completely run out of cycles, because at some point you can't expect the data to just be held around for free. So
Yeah, that's good. Okay, yeah, thank you.
yep.
Yeah.
Yeah, it doesn't look like there's any questions, so I guess my part is done. So I'll hand it back over to you.
Yeah, no, we can wrap it up. Thank you so much, guys. Thanks, Jordan. Thank you, everyone, for your time. And yeah, have a good Sunday. Or in China, have a good evening Sunday. For the rest, enjoy your day tomorrow and have a good night. See you. Thank you so much. Bye-bye.
See ya.